Okay, so our first talk of this session is Siddharth Hari Haran. I hope I've got that right, from Imperial College, and he will be talking about partial fraction decomposition for certain fractions of polynomials. So, without any further ado, please carry on.
Yeah, thank you so much. Hi everyone, I'm Siddharth. You can call me Sid. And I'm going to talk about partial fraction decomposition for a certain specific class of ratios of polynomials. And I'm going to, in particular, focus on how it can be done formally as it would be done in the programming language Lean. More about that in a bit. So first of all, just a simple question to everyone. How would you go about simplifying the following? And feel free to enter an answer in the chat. Any suggestions? No? Anyway, so one way that you could simplify this is by using partial fraction decomposition, right? As the name suggests. Yes, indeed, as Toby says, you do partial fractions. You can actually do them on both of them. So you split up these polynomials in the denominator, you factorize them, and then you separate them into things that look like this, into terms that look like this, and then you can evaluate them the way you would. You know how to integrate probably a lot better than I do. So yeah, and the second one just becomes a telescoping sum. So it's a very natural question to ask, right? Which is, how do we know that you can do this sort of a decomposition? Because in high school, we were taught that if we've got an integrand that looks something like this, we just write it out as 1 over this thing times this thing. And then, we can write that as a over x plus 2 plus b over x plus 3 and solve for a and b. But how do we know that such an a and b even exist? It's a very natural question to ask. Under what conditions can we thus decompose fractions of polynomials? And our goal today is therefore going to be to, first of all, understand what properties are sufficient for a decomposition to exist. Secondly, to then prove that a decomposition does indeed exist when we expect it to, i.e. when these properties are satisfied. And thirdly, to explore the intricacies of formalizing this result in Lean. So what is Lean? A little bit of background coming up. So simply put, Lean is a programming language. It's a functional programming language in particular, and it's got its origins in something known as dependent type theory, which is a sort of type system that's used. You can think of it as sort of being analogous to the ZFC system, which is conventionally viewed as the foundation of mathematics, right? Those are the axioms from which we build up also all of our complicated mathematical constructions. In Lean, we use a foundation known as dependent type theory, and sort of everything is sort of modeled along this idea. It's not very important to get into the details of it, so you can always read up on it online if you're interested. And in Lean, we have objects, definitions, theorems, and proofs. And objects would be, well, it's not necessarily objects in the same sense as object-oriented programming, but you have these constructions. You can have sets, right, which would be referred to as types. And you can have objects that belong to sets, which would be referred to as terms of some type. So natural numbers are a type, and 1, for example, would be a term of the type nat, or natural numbers. And then you can have definitions, right? You can define what it means for a certain object to have a certain property, right? And then you can have theorems, just as you would in mathematics, which tell you that given certain conditions, you have a certain conclusion. Given a set of hypotheses, you can come up with a certain conclusion. And considering that Lean is a functional programming language, if you guessed that theorems are formalized as functions, you'd be absolutely right. Because what you do is, a theorem is essentially written as a function that takes as input a bunch of hypotheses and gives as output a bunch of conclusions. And the proof of a theorem simply becomes the algorithm that takes these hypotheses and turns them into an output. It's a step-by-step procedure from hypotheses to conclusions, just as would be the case with a mathematical proof as well. And the long-term goal, why mathematicians are really interested in Lean, is that we want to create sort of a unified digital repository of the mathematics that we know. Because this allows, this makes it very easy to sort of look up mathematical results, to see under what conditions they are true, to sort of go through results in more and more depth, because in a code editor, you can always see the definition of a function, right? And if that function uses other functions, you can see the definitions of those functions, and so on and so on and so on. And this in particular means that somebody who's reading something in which they don't have much background can actually go and look at all of the definitions until they reach a point where they're actually comfortable with what's going on. And this is quite different from what we have at the moment, with mathematical papers being sometimes very inaccessible to undergrads like you and me. So yeah. As for some of the conventions that are used in this gigantic repository, MATLib, well, it can essentially just be viewed as a piece of software, which means that all of the conventions that we use when committing to MATLib sort of resemble just good programming conventions in general, right? Because in general, for example, you would want to inherit or reuse code rather than duplicate it. And the same is true of MATLib as well. And this means that when you formalize a theorem, you want to do so in maximum generality, so that if you've got a special case of that theorem, then you can simply specialize whatever theorem you have with the specificities of what you're looking into. And finally, you would want to optimize code, meaning that you would want to call certain functions in the most efficient form. So you wouldn't want to call a function that searches through the library and gives you, I don't know, a result at the end. You would do that initially, maybe, and then you would take the result that it's given you, and you would just substitute the search sort of command with whatever you've come up with. And that's actually known as a tactic, but I don't want to get into any technicalities here. So what I'm going to do is I'm essentially just going to run through the basics of the proof, okay? And I'm going to sort of give you an outline for how you might strategize, how you might sort of structure a proof in Lean, but I won't actually show you any code, but I will be linking to the GitHub at the very end, so you can always see the file that I wrote over the course of the summer when I worked on this. So why are Lean proofs different from mathematical proofs? Well, the answer is that mathematics is usually done quite informally. Now, I want to make an important distinction here between rigor and formality, because mathematics, as we have in the literature and as we're taught at university, is definitely very rigorous. That said, it tends to be informal in the sense that it doesn't sort of go into too much detail, and it sort of allows us to gloss over certain things. And I have an example over here, right? We say things like the integers are a subset of the real numbers, right? But that's not actually true in the strictest sense, because the way that we define the integers is very different from the way that we define the real numbers. The integers are defined in terms of ordered pairs of natural numbers, whereas the reals would be defined in terms of Cauchy sequences of rational numbers, or in terms of Dedekind cuts, or whatever definition you prefer. Therefore, what we're actually trying to say is, well, there is a ring structure on Z, there's a ring structure on R, and indeed, there is an injection that sort of respects this ring structure that goes from Z to R, and that's really what we mean. The difference then is that the Lean compiler, so when you put in a proof in Lean, it actually checks your proof down to the axiomatic level. So that means that, as I said, that's one of the reasons why it's so useful, because you can sort of go into an argument in as much detail as you would like. So that means that in particular, when we want to teach a proof to Lean, that is, when we want to formalize a result in Lean, we need to lay out our argument in a manner that it can actually understand. And this is going to be the challenge. So we can now plan our strategy to prove partial fraction decomposition the way we would in Lean. So we'll define a bunch of terms, then we'll state without proof a few results we'll need, and then we'll prove the theorem. And this actually mirrors the structure of the document of the Lean file that I wrote, which you'll be able to get at the end. Because at the very beginning of the Lean file, we've defined a bunch of variables, and then instead of stating results, we've just called results that are already in the library, because they're just functions at the end of the day. And then we prove the theorem. Of course, that's the main part. We'll also look at some of the intricacies as to why the Lean proof is slightly different from the mathematical proof. So without further ado, let's get into the maths. So first of all, the coefficients of polynomials typically come from rings. And for those here who might not be familiar with what a ring is just an abelian group with a multiplication that's associative and that has an identity, and that's just well behaved in certain senses. But you don't necessarily need the multiplication to be commutative, and you don't need it to admit multiplicative inverses. So we've got something known as a domain, right? And a domain is simply a ring without zero divisors, in which case, which equivalently just means that if you have A and B that are non-zero, their product is non-zero. And you have something known as an integral domain, which is just a domain in which the multiplication is actually commutative as well. Indeed, in Lean, there is no sort of concept of a ring being an integral domain. You would define it as being a domain and then as being commutative. So you define those separately, and that amounts to it being an integral domain. So I'm literally following the structure of the Lean file here. So polynomial rings, well, indeed, a polynomial, well, if you look at the set of polynomials in one variable with coefficients in an integral domain, that actually inherits an addition and a multiplication from said integral domain. Indeed, it is itself an integral domain. This is all fairly straightforward to prove, so I'm not going to prove it. And yeah, indeed, X does not actually have to belong to R, and I'll leave it to you to think of examples where indeed you apply polynomial to something that's not in your integral domain R. So what does it mean for a polynomial to be monic? That simply means the leading coefficient has to be 1. And we've got hundreds of millions of examples of monic polynomials. So you can always think of those. What does it mean for two polynomials to be coprime? Well, depending on your background in ring theory, you may or may not have seen different definitions of coprimality of polynomials. I've chosen to stick with the definition that's given in MATLAB, which is that two polynomials in Rx are coprime if there exists A and B such that AF plus BG equals 1. Indeed, for those of you familiar with number theory, this might look a little bit like Bézout's lemma. And indeed, there is another definition of coprimality of polynomials, and there is an extended version of Bézout's lemma that you can use to prove that this definition and that definition are indeed equivalent. So indeed, we'll find that expressing coprimality in this format is actually particularly convenient for the problem we want to solve. So a few useful results. Well, here's a theorem. This is nothing but all this says really is that your polynomial ring over an integral domain is a Euclidean domain. In other words, you can do Euclidean division. You can prove that you can do Euclidean division pretty much the same way that you would prove it in the integers. It's not that different. You have another lemma over here where you say that if F, G, and H are in Rx, and if F, G, and F, H are coprime, then F and GH are coprime. And indeed, I've also mentioned how these results are given in MATLAB. So indeed, in my Lean proof, I simply apply these results. I apply a slightly more general version of the second lemma. But yeah, you can prove this lemma just the way you would over the integers. And now we come to the main result, which is the partial fraction decomposition theorem. So we have two conditions here that we need on our F and on our GI. Well, actually, the conditions are just on the GI. So we need the GIs, first of all, to be monic. Second of all, we need the GIs to be pairwise coprime. That means if I does not equal J, then GI is coprime to GJ. And coprime is just this definition here. So then what the theorem says is that there exists Q R1 up to Rn such that the degrees of the Ri are less than the degrees of the GI, and we can express F divided by the product as equal to Q plus this sum over here. Now, in my proof, I'm not really going to prove this bit because this is pretty straightforward. It follows very naturally from the Euclidean algorithm. And indeed, the entirety of the proof is going to pretty closely resemble the Euclidean algorithm. So the way that we're going to approach this is by proving the case for two denominators and then proceeding by induction. And we'll see why the two denominators case is important. So if we've got two denominators, G1 and G2, then we know that these two guys are coprime, and therefore we can apply that Bézout's lemma sort of definition of coprimality to write this. And then we write F equals F times 1. And indeed, these are actually explicit lines in the Lean file. So I've very, very literally copied and I've replicated the format of the proof. Then all you need to do is you need to make that substitution over here, do a little bit of arithmetic, and then apply the Euclidean algorithm and collect terms, and you're done. So it's just a matter of arithmetic. Yeah, and then you can actually then proceed by induction on n. The n equals 1 base case follows from the quotient remainder result from the Euclidean algorithm. In lean, it's a little bit different, and we'll come to that at the very end of the talk. And what we do is we assume the result for general n, we convert it into a 2 denominators case like so, and then we apply the previous result, and then we're done. So that's pretty much it. But see, things are not so easy in lean. I really wish they were, but they're not. And there's mainly two things that are different in lean. First of all, we use a slightly different style of induction, because induction has been sort of the bedrock of of this argument here. That was the style that we used to approach it. Secondly, there is a distinction between an integral domain and its field of fractions that I completely glossed over, and that lean would not allow me to gloss over. So we'll talk about that in just a bit. Firstly, induction in lean, the new convention of doing induction is to use something called fin sets, because it allows us to maximize generality. So our G1 up to Gn are nothing but instances of some map G that goes from the natural numbers to Rx, right? And in this case, we simply substitute the natural numbers with some arbitrary type iota. Iota doesn't have to be finite, it doesn't have to be countable. It could be the complex numbers for all we cared. And what we do is then we look at arbitrary finite subsets S of iota. And then we look at sort of the restrictions of this map G over that finite set S. And that's really what we start caring about, because we take sums and products over S. We can't really deal with infinite products or infinite sums because we don't necessarily have a topology, which means it may not necessarily be a sensible thing to talk about the convergence of an infinite sum when we're working over an arbitrary integral domain. But anyway, the base case in this kind of induction is to say, well, let's think about different kinds of subsets iota. The base case is when that finite subset of iota is simply the empty set, right? And this actually makes base cases very easy to prove in lean, because sums over the empty set are simply 0 and products are simply 1. So it's very, very convenient indeed. And then there's an inductive case where it exactly resembles what we would expect. It says, let's say that it's true over some fin set. Then what you can do is you say, okay, let's take an element of iota that's not in this fin set. Let's call this element A, and let's insert it into let's insert it into B. Right. In other words, we assume the result for B, and then we prove the result for B union some singleton containing A, where A is not in B. And that's how we do induction. And it's particularly important to pay attention to where you quantify your terms, because otherwise in lean, things can get extremely messy. And this actually threw me off at the beginning when I was working on my proof. Then there's an important distinction between an integral domain and its field of fractions, because if you recall, I mentioned that an integral domain does not necessarily have inverses, but then we looked at fractions of polynomials. So there's something kind of funny going on there, because we're dividing by polynomials, even though we don't have a well-defined notion really of what it means to divide by a polynomial. So what we want to do is we indirectly want to sort of move into a structure where you have these ratios of polynomials. But this is a pretty terrible definition, even from a mathematical sense, because there's no definition of divides. So what does it mean to say P over Q? That doesn't make any sense whatsoever. And that's why what we do is we make a few observations. Firstly, any P over Q consists of two elements of the ID, which is P and Q. Secondly, Px over Qx would be equal to P over Q. This is what we would expect, at least, provided X is non-zero, of course. So each element in this field of fractions is not actually given by a unique pair P comma Q. So what we do is we simply define an equivalence relation. We essentially look at what we would intuitively expect, which is this thing over here. And then we define this equivalence relation, and we look at the Cartesian product J over here, and we quotient out by this equivalence relation, and that gives us our field of fractions. And the word field is used very deliberately, because this is indeed a field, and that's easy to verify. So a couple of things to note: this identically mirrors the construction of Q from Z, and the reason why we need R to be an integral domain is so that we don't get 0 in the denominator when we multiply two fractions together. And it is improper to say that R is a subset of K, because what we really mean is that there's an injective ring homomorphism going from R to K. So this is something that Lean really picks up on and that Lean really insists on. So the issue really is that all of the lemmas that we stated earlier in Lean are defined over Rx, whereas the theorem that we want to prove is in the field of fractions. So what we need to do is we need to apply this injective homomorphism everywhere, and that can get a bit annoying, but that is just something to take care of, and there are tactics to sort of help people do that in Lean. So this is typically expressed as something called a coercion, and I won't get into any details here because we're running out of time. So concluding remarks, this is what we've seen today. We've seen how to prove this result. We've seen what Lean is about, and we've seen some of the intricacies involved in formalizing and proving this result in Lean. So that's pretty much it from me. And I'm not sure if we have time for questions, but I'll quickly change the slide here so you can always scan these QR codes and look at the MATLAB file that I wrote under the supervision of Dr. Kevin Buzzard at Imperial. And you can look at these slides at your own pace by scanning this QR code over here.
Okay. Oh, thank you very much for your talks. It was very, very interesting. We have a question from James Fawn.
Hello there. I just wanted to ask about the axiom of choice and how that works with Lean. Is it hard coded into the library, or do you choose whether you want to believe the axiom of choice or not before you try and prove something?
That's an excellent question. So the thing is that before Dr. Buzzard actually sort of got involved in all of this, it was mainly computer scientists who were working on MATLAB, and computer scientists in computer science, typically, I think they were more interested in not allowing the axiom of choice. But then Dr. Buzzard pointed out that a lot of mathematical proofs require the axiom of choice, even things like taking quotients. It sometimes requires choice. And that's why whenever you have whenever you're stating a theorem in which you need to use the axiom of choice implicitly, you mark it as non-computable, and then you can sort of proceed like normal. So the axiom of choice is indeed allowed in Lean, but you would not mark something as non-computable unless you absolutely had to. Does that answer your question?
Yeah, that's really interesting. Thank you.
Yeah.
Okay, I think we'll wrap it up there. If anyone has any further questions for Sidrup, I think you can catch up with him later on in one of the breakout rooms.
You can write to me as well.
Yeah.
My email address is over here.
Okay, great.